Thanks to Brilliant.org for supporting PBS Digital Studios. This is the golden ratio, phi. It gets a lot of attention. But what about the silver ratio? Cut a line segment into unequal pieces of lengths A and B, such that the ratio A to B is the same as the ratio A plus B to A. That is, so that the whole big segment over the medium piece equals the medium piece over the small piece. This is how you construct the golden ratio, phi. If a rectangle has an aspect ratio of phi, then you can subdivide it forever into a square and another golden rectangle at each level, and you can make fun logarithmic spirals by connecting the corners. Now instead, let's make two medium pieces and one small piece out of our original segment, such that, once again, big over medium equals medium over small. This is how you construct the silver ratio, or silver mean. You can even play the same rectangle and spiral game, with two squares at each level of subdivision. Okay, now keep incrementing the number of medium pieces, or squares in the rectangle picture, while always requiring that big over medium equal medium over small. You then produce a whole sequence of so-called metallic ratios, or metallic means, the nth one of which I'll denote as sigma n. Now the golden ratio hogs all the press, so you may be less familiar with its mathematical metallic cousins. And that's unfortunate, because many of the sexy mathematical features commonly attributed solely to phi actually have equally cool analogs in the rest of the metallic ratio family. And that's why we're doing this episode, to showcase these analogs so that you can explore them further if you feel inclined. But please watch all the way through to the end, because I'm going to end with a feature of phi that I'm not quite sure does generalize to the other sigmas, and I'm hoping some of you will be able to help figure it out. Let's start with the defining equation for the golden ratio. It can be rewritten as phi equals 1 over phi plus 1. In other words, the golden ratio is one more than its reciprocal. With a little algebra, we see that this condition is equivalent to the quadratic equation phi squared minus phi minus 1 equals 0, which has two conjugate solutions, one of which is positive, one negative. Now since phi is the ratio of two lengths, it has to be the positive solution. That's 1 plus the square root of 5 all over 2. But the conjugate solution isn't exactly a throwaway. Notice that phi plus its conjugate equals 1. And going back to our original equation, that phi minus its reciprocal also equals 1. So apparently, the conjugate of phi is the negative reciprocal of phi. Okay, all of the above properties generalize. Watch. The defining equation for the silver ratio sigma 2 can also be rewritten as sigma 2 equals 1 over sigma 2 plus 2. So the silver ratio is 2 more than its reciprocal. More generally, sigma n is n more than its reciprocal. Again, you can encode this condition into a quadratic equation that differs from phi's quadratic equation, only in that its linear coefficient is now minus n instead of minus 1. And once again, you find two conjugate solutions of opposite signs. Sigma n will be the positive one. That works out to n plus the square root of n squared plus 4 all over 2. And again, sigma n's conjugate turns out to equal its negative reciprocal. Here's a table of all these values for the first few n, just for reference. Now let's connect this to some number theory. One way to represent real numbers is with continued fractions, which are basically nested layers of fractions inside fractions. For example, pi can be written as 3 plus 1 over 7 plus 1 over 15 plus 1 over 1 plus 1 over 292 plus, and so on forever, since a continued fraction of an irrational number is infinite. Rational numbers, in contrast, have finite continued fractions. For instance, 1 plus, 1 over 2 plus, 1 over 3 plus, 1 over 2. Now, as long as we agree to use only ones as numerators, continued fractions are unique. But some continued fractions look cooler than others. For example, 1 plus, 1 over 1 plus, 1 over 1 plus, 1 over 1 plus, and so on, just infinite ones all the way down the chain. What number x does this correspond to? Well, notice that if we zoom in on the first denominator and blow it up, it looks identical to the entire continued fraction. So whatever x is, it's apparently equal to 1 plus 1 over x. But wait, that's just the defining equation for phi. That's pretty neato. Okay, what if we had 2's all the way down? This would represent a number that is 2 more than its reciprocal by similar logic, i.e. the silver ratio, sigma 2. Now extrapolate. The nth metallic ratio, sigma n, must therefore be the number whose simple continued fraction consists of n's all the way down the chain. And here we see yet another example of a property that is not specific to phi. Now, there's a cool connection between phi's continued fraction and the Fibonacci sequence, each term of which is the sum of the previous two, starting with 1 and 1 as seed terms. The sequence of ratios of successive Fibonacci terms is well known to tend toward phi in the infinite limit, but why does that happen? Well, consider a geometric sequence in which each successive term is exactly phi times the previous term. So for example, 1, then 5, phi squared, phi cubed, and so forth. Notice that the third term, phi squared, is exactly the sum of the previous 2 terms. Just look back at the quadratic equation that phi satisfies. If you keep multiplying that equation by phi, you see that every term in this sequence is the sum of the previous 2. In other words, a geometric sequence whose term ratio is phi will automatically satisfy the Fibonacci recurrence relation. So any sequence satisfying this same recurrence relation will get closer and closer to being geometric with phi as the term ratio. This includes not just the Fibonacci sequence, but any sequence satisfying this same recurrence relation, regardless of the starting values, like for instance, the Lucas numbers. But among all such sequences, there's something quite special about the Fibonacci sequence specifically. Namely, go back to the continued fraction for phi and cut it off after 1 nesting level, and then after 2 nesting levels, then 3 nesting levels, and so forth. The terms you get are the best rational approximations to phi with that denominator or lower. And lo and behold, those are precisely the ratios of successive Fibonacci terms. But once again, this coolness is not the sole purview of phi. Let's imagine a geometric sequence with a term ratio of sigma n. Looking back at the defining equation for the nth metallic ratio, we can see that each term in this sequence will be n times the previous term, plus the term before that. So now let's make a Fibonacci-like sequence that satisfies this recurrence relation, with seed terms of 1 and n instead of 1 and 1. And let's list the ratios of its successive terms. Once again, you get the successive finite cutoffs of sigma n's continued fraction, which is pretty cool. So that's my whirlwind tour of the metallic ratios. We touched on some geometry, some algebra, and some number theory. Here's a summary of the properties that we discussed, but of course that just begins to scratch the surface. There is a lot of fun structure to explore here, and I encourage you to do so. I myself started toying around with the following question, which I have not yet managed to answer conclusively. So the golden ratio is known to feature prominently in the regular pentagon. Specifically, the ratio of the diagonal of a pentagon to its side is 5. Now the silver ratio, sigma 2, makes a similar cameo appearance in the regular octagon. It's the ratio of the octagon's second diagonal to its side. But what about beyond that? Are any of the sigma n's equal to any diagonal to side ratio in any regular polygon? I've coded up a crude numerical exploration for sigma 3 and found nothing so far. But what I'd really love is either a proof that it never happens or an explicit example of when it does happen for at least one sigma n. Now, this is an open-ended question. I don't know the answer. But if any of you feel inclined to search and come up with one, then A, publish it, and B, please email us to let us know. We'll shout you out in a future episode and send you some PBS swag. Until then, good metallic hunting, and I'll see you guys soon. In the episode you just watched, I posed what is, as far as I know, an open problem concerning metallic ratios and regular polygons. Now, some open problems are crazy hard, but some just happen not to have been tried much yet. I don't know which category my problem falls into, but I do know that trying problems that no one has successfully answered before is one of the best ways to get a taste of how mathematical or scientific research actually unfolds, that it can be scary, but also thrilling. This is another reason I like Brilliant.org. They have a whole group devoted just to open problems, from topics in geometry, number theory, basic logic, and more. Now, tackling them probably won't get you a Millennium Prize because most of these problems are specific in their scope, but that's how real-world research progress happens. You take a big open problem and break it down into lots of smaller open problems, which may give you or others insight into yet other open problems, and so forth. So check out Brilliant's Open Problems group. Collectively, it's managed to solve the 3x3 anti-magic square problem, which previously only had computer solutions that involved a lot of tedious case checking. It's a great resource for getting real-world exposure to what research without a safety net feels like. So explore Brilliant and support Infinite Series by going to brilliant.org/Infinite Series to sign up for free. The first 200 people using that link will get 20% off the annual premium subscription.
Hey everyone, Denee here. So, I read your comments from Brouwer's fixed point theorem, and I know you want more information. Good! I'm glad to hear it. And I'll be the first to tell you, I left out a ton of detail, so you have every right to demand more. In fact, that's exactly what a mathematician should do, so bravo. Let me start by saying that there were a lot of new, complex ideas going on, but I chose to cast a wide net in that episode. I wanted to present the proof in a way that would be accessible to a very broad audience, but I also have a time constraint to work with, so I had to cut out a lot of detail that I wanted to share. As a result, that left the proof feeling incomplete. I absolutely get it. So let me try to fill in some of those gaps now. Chi W, like most of you, wants more detail about the portal or the functor that we used in the proof. How does it actually work? Well, it's a mouthful, so get ready. This functor assigns a particular group to each topological space called the fundamental group. The elements of this group are constructed by taking equivalence classes of continuous functions of the circle into the space, aka loops with a fixed base point, where two loops will lie in the same equivalence class if there is a homotopy from one to the other. That is, if one loop can be wiggled to the other. The group operation here is determined by loop concatenation, which we've talked about before. Now, the two topological spaces we saw, a disk and a circle, each have their own fundamental group. The fundamental group of the disk is 0, or the trivial group, because there's only one equivalence class, namely that of a point. In other words, every loop in a disk can be contracted or homotoped or wiggled down to a point. This is why the disk was assigned the number 0. On the other hand, the fundamental group of the circle is isomorphic to the integers. Why? I gave an intuitive explanation in the video, but the formal proof uses some really heavy machinery like covering space theory. So, if you're interested in the details, there are 6 links in the description of the Brouwer video, so definitely check them out. Okay, back to this functor business. Ankit asked why the map from the integers to 0 is analogous to the map from the circle to the disk. Fantastic question. So, not only does the functor assign fundamental groups to spaces, it also makes an assignment on the functions between them. Every continuous function between two topological spaces gives rise to a group homomorphism between their corresponding fundamental groups. So for example, a continuous function from the circle to the disk gives rise to a group homomorphism from the integers to 0. And a continuous function from the disk back to the circle, like that function h, gives rise to a group homomorphism from 0 back to the integers. Moreover, the key property of this functor in all functors, and this is what we use in step 3, is that the group homomorphism corresponding to the composition of what I call the boring function, really it's an inclusion map, with the continuous function h, this homomorphism is equal to the composition of the homomorphism defined by the boring function with the homomorphism defined by h. This is how the portal works, and it's a lot to digest. None of it is obvious, and it all requires serious work to explain and to prove. But if you're interested in unwinding it all, and I hope you are, I recommend putting pencil to paper and re-listening to the past few minutes, maybe a couple times, and digging through the references provided. By the way, Dark Chaos 110 astutely pointed out that I did not prove that h is actually continuous, but it absolutely is. A small change in x corresponds to a small change in h of x, and this relies on the continuity of g. It's a great idea to go back to the video and convince yourself of this. Good catch, Dark Chaos. Okay, I'll stop here because as you can see, it's a lot to swallow, but don't hesitate to check out the links provided in the Brouwer video. And the next time we dive into such a high-level topic, I'll be sure to tell you exactly when and where I'm omitting details and where you can look them up. See you next time.